Look at our strong acids versus weak acids here. An acid's strength is determined by what percentage of its H pluses dissociate or break off of the compound and end up in the solution. So weak acids dissociate less than 5%. So if you had 100 molecules, only 5 of them, or less than 5 of them, would have the H plus break off the molecule and go float around in the solution. So like acetic acid would be an example of one. Acetic acid or vinegar, in vinegar, there's very little bit of it, of the actual acid. Most of it's still in the CH3COOH form. Only, I think it's 3% of it has got that H that's detached and become H plus in there. Other weak ones are water, can be both an acid and a base, it's a weak one, and hydrogen fluoride, also weak. Strong acids, on the other hand, dissociate fully or completely. Every single H plus you put, every single compound you put in there will break apart into its ions. The negative ion plus the H plus ion. Those examples would be nitric acid, sulfuric acid, hydrochloric acid, etc. So let's ask a question like this. What would have a lower pH? 100 milliliters with 100 HCl molecules in it, or 100 milliliters with 500 HF molecules in it? Take a minute, think about it, hit pause, see if you can come up with one of them and why you think it might be that. Alright, let's see. If we have 100 milliliters of 100 HCl molecules, we'll have a molarity. Well, I guess we don't have moles of it, but we can think of it like a concentration. So not molarity per se, but concentration is going to be, alright, of those 100 HCl molecules, since it's a strong acid, we have 100 H pluses in solution. That's divided by 100 milliliters. So let's say it's a concentration of 1. No real unit, because it's not actually in moles or liters, but we'll go with it. Now in this case, we still have 100 milliliters for HF. So it's still 100 milliliters. We have 500 molecules in there. So you go, alright, well there's more molecules, so maybe then that one's got a lower pH because it's got a stronger concentration. However, HF is a weak acid. So only 5% of those molecules are going to break into H pluses. So we got to take that 500 times 5%, or 0.05. You only get 25 molecules to be in there. So in this case, we have 25 over 100 milliliters. It only gets us 0.25. The 100 HCl molecules have a concentration of 4 times stronger, so it's going to be a much lower pH. Alright, if we're combining acids and bases, we need to figure out what the new volume is going to be, what the new molarity is going to be, how they're going to change. Do this in titration type labs. Here's an example question. If you have 200 milliliters of an 8 molar sodium hydroxide solution, and you want to make it a 2 molar solution, what volume must you add of water? Or to what volume must you add the water? So our formula is going to be M1V1 equals M2V2. The M stands for molarity, as we've used before, and the V stands for volume. As long as these volumes are in the same unit, we don't care what the unit is. Both milliliters, cool. Both liters, cool. One's different though, you need to convert them until they are in the same unit. So with this, and this formula, see if you can solve this question. If you haven't hit pause ready, do that. In a second here, I will work through it. Alright, so we have 200 milliliters is our V1. 200 milliliters, and we also know it's an 8 molar solution. So M1V1, we're good. Equals, well, we know we want it to be a 2 molar solution, so that's our M2, but our V2 we don't know. To solve for it, algebraically, we must get V2 by itself. So we divide this side by 2 molar, divide this side by 2 molar, that'll cancel, V2 equals 8 molar times 200 gets you, stop doing that, thank you, no, 1600 over 2 molar equals 800 milliliters. So our molarities have canceled. We're left in milliliters then. It should be that. So our second volume needs to be 800 milliliters of it, so we should get the red one. Hopefully you did as well. Let's look at another one. If you have 300 milliliters of a 12 molar HCl solution and you want to make it a 1.5 molar solution, how much water must you add? No, it's in bold. It's a slightly trickier question. There's your formula again. Here are your possible answers. Pause it, give it a shot. When you think you have it, then hit play again. Hopefully you got 2100 milliliters, but I'm guessing some of you got 2400 milliliters. Let's figure out why. Alright, so M1V1 equals M2V2. They give us a 12 molar acid times 300 milliliters of it, and we want it to become a 1.5 molar solution, and we don't know what the V2 needs to be. Alright, well, again, we get V2 by itself, so we're going to divide the whole thing by 1.5 molarity, which then means V2 is going to equal 12 molar times 300 milliliters divided by 1.5 molarity. Molarities cancel. Do our math. We take 12 times 3 divided by 1.5 gets us 2400 milliliters. Shows you, yeah, see exactly. There's our volume. It should be 2400 milliliters. But that's our total volume. Note, we already have 300 milliliters from our original solution. So we need to take the 2400 we need minus the 300 we already have, because we're just adding the water component to it to get our 2100 milliliters for the answer. One last one. If we have 700 milliliters of our base, so V2 is going to be that. Well, M1 V1 equals M2 V2. We know our original molarity is going to be 5 molar. That's our base. Times our original volume, 700 milliliters. Equals our second molarity. We have 3 molar acid times an unknown volume. We need to figure out what our V2 is to find our amount of acid we need to add to neutralize or make the base go away. Again, to make our V2 work, we need to divide by what's also on that side with it. If this thing will ever not bring up that thing. So we divide both sides by 3 molar. They'll cancel on this side. When we do the math, V2 is going to be the 5 times 700 divided by 3. Going to get us 1066.67 milliliters. Or you're answering green. And the last part of this objective, naming acids. Alright, let's name these suckers. Here's a little chart that you might want to have down that helps you figure out what you need to do. If the ion ends in "-ide", so if we have like over here on the right we have HCl. So we're going to ignore the H's when we name this, because they all have to have H's, they're all acids. So HCl here, the other part of it is the anion chloride. Or chlorine, when it's in the compound, is called chloride. Since it ends in "-ide", we're going to add the prefix hydro out front, so hydrochlor, and the ending goes to "-ic". So hydrochloric acid would be the name. So that worked for any lone element. So any lone nonmetal, sulfur, fluorine, chlorine, bromine, nitrogen, take your pick. And then 1 or 2 on the back. There's the weird ones of hydroxide, that's a multiple element, and cyanide. Those ones are also going to be named hydro, whatever it is, ic acid. However, if it ends in 8, so like PO4, that anion is called phosphate. That one has no prefix whatsoever. It's just going to be phosphate, but the ending goes to ic. So it's in this case, phosphoric. It's a little bit weird. You give me phosphic, I'd understand. There's 2 weird ones, the phosphorus and sulfur. So phosphate and sulfate are both phosphoric and sulfuric acid. But either way it'll work, I'll take it. So if the polyatomic ion, if the anion, the non-H part, ends in 8, you add the ending to ic, and that's it. The last one is ite. So, like, this case, SO3, that anion group, the one that's not the H's, is called sulfite. So, again, there's no prefix for this one. So it's still sulf, but instead of sulfite, it goes to us. It becomes sulfus acid. Little hints or tricks of how to remember these. Alright, in the cafeteria you ate something icky. Ate goes to ick. The other one, the old saying when I was a kid was, bite me. Well, we're in this class, we're in this together, so not bite me, but we're going to go bite us. So you can bite us, buddy. We're done. Let's try a couple practice ones of these. So what's the name of the following acid? There's your acid. Pause it, give it a shot, we'll check the answer, see if you're right. Alright, so when we're naming this one, hopefully you got this. And why that is because CrO4, the non-H part, right, we can kind of ignore that when we're naming it. CrO4 is called chromate. And you ate something icky. So it goes from chromate, to chromic, and we add acid to the end. So chromic acid. This one, HClO2. Okay, try it again, hit pause, figure it out, then hit play. This one you should have gotten chlorous acid, because again, we know the H, the ClO2 part, it's called chlorite ion, and chlorite, we tell them to bite us. So it goes to not chlorite, but chlorus acid. And if we look at H3N, try that one again. Pause it, figure it out, hit play, and check your answer. Alright, so again, we ignore the H's. We have just one lone element. So that ion would be called, from nitrogen, becomes nitride. So ide, if it ends in ide, we have to add that hydro prefix. So hydro, then nitride, the nitride, ide goes to ic, so hydronitric acid. There's all your pH and naming things. Got questions? Let us know.